Okay, we had talked about last time concentration of solutions. We talked about molarity, just a brief review. Moles of solute over liters of solution. So that's one term of concentration. I can never get this thing to... And of course we did this problem with the glucose. I gave you the weight. So to calculate the molarity, you have to change the amount to moles, and then divide it by the liters of solution to give you the molarity. And then the other two parts are just rearranging that molarity equation, given the molarity in B and the number of moles, you could calculate the volume you needed. And in C, if you're given the volume and the molarity, calculate the number of moles you had. So now we're going to talk about dilution. That's the process of preparing a less concentrated solution from a more concentrated one. We do it all the time. You go to the grocery store, or you buy a clean solution that says, dilute 1 cap full per quart of water. So the moles of solute before dilution equals the moles of solute after dilution. You haven't changed the amount that's dissolved, you've just changed the amount of solvent. So how do you calculate that? We can say the molarity of the concentrated solution, that's what the subscript C means, times either the liters or milliliters of the concentrated solution is the molarity of the diluted solution times the liters of the diluted solution. And you can use liters. If we use milliliters, we come up with a term called millimoles, which is molarity times milliliters. So if you're using this dilution formula, as long as your concentrations are in the same units and as long as your volumes are in the same units, it works fine. So you have to make sure they're in the same units. So here the question is, what volume of a 12 molar HCl solution must be used to prepare 250 milliliters of a 0.125 molar solution? Well, using this formula, what's the molarity of the concentrated solution? 12. So it goes here. We don't know the volume. We want to know how much we need. So we're still going to have liters, or in this case, well, milliliters we need to use. So what is the molarity of the final solution we want? 0.125. And how much of it do we want? 250 milliliters. So our concentration of our stock would be 0.125 times 250 milliliters over 0.0. And if you do all the plug and chug, you get 2.60 milliliters. So if you want to make the solution, you take your stock solution, take 2.6 milliliters, put it in some container, dilute it to 250 milliliters with water, and your final concentration would be 0.125. Any questions on any of that? I mean, you can kind of think about it, if you have a concentration of 5 molar and you increase the volume by twice, the concentration then becomes 2.5. If you double the volume, you half the concentration. A lot of times what we do in chemistry, especially analytical, is something called serial dilution, where we take a stock solution here on the left, and we make, okay, here we're making the first dilution. Then we take some of the first dilution and make a second dilution. Then we take some of the second dilution and make a third dilution. Third dilution and make a fourth dilution. So now we end up with 4 different concentrations. You can see that the flats get lighter in color as we go from left to right. So here we're starting with a 2 molar stock solution of HCl. We're going to make 4 standard solutions. We're going to dilute 10 mLs of each solution, 250 milliliters. So we have to determine the 4 standard solutions. So the molarity, using the same equation, but we see it here rearranged, the molarity of the diluted solution is equal to the molarity of the concentrated solution times the milliliters divided by the milliliters of the dilute. So for, let's see what we got here. We had 2 molar. We're going to take 10 milliliters out of that. So for the first one, it would be 2 molar times 10 milliliters. We're going to dilute it to 250 milliliters. So for the first one, the new stock solution would be 2 times 10 divided by 250. So the first solution would be 8.00 times 10 to the minus 2 molar. The second one, we're going to take 10 milliliters of that solution and dilute it to 250. So the second solution would be 3.20 times 10 to the minus third. The third solution, we would take 10 milliliters of the second solution, dilute it to 250, so we get 1.28 times 10 to the minus 4. The fourth solution, we take 10 milliliters of the third solution and dilute it to 250, so we end up with 5.12 times 10 to the minus 6 molar. Are we okay with that? We're just changing what becomes the diluted solution becomes the concentrated solution in the next step, and so forth. So it's a serial dilution. So we do this in chemistry a lot, so we can generate what's called a calibration curve. And if we take these solutions and put them, this is not covered in your book, this is just a side, in a spectrophotometer and look at their colored solutions, so they're going to absorb light. And we plot the absorbance versus the concentration. We get a straight line. So here's our 4 solutions. And this is called Beer's law. Beer is in drinking, B-E-E-R. Had nothing to do with drinking. So now we have the standard solution. So somebody brings me an unknown concentration and go and measure its absorbance. Let's say it's here. I can go over to this line and then down, and I can tell you what its concentration is. So that's how we use it in chemistry. Make a standard curve, and then do an unknown. And if you do 150, Chem 152, we're probably going to do that this year. So part B was to figure out how many moles. So if we look at the first solution, it was 0.0 times 10 to the minus 2 moles. Remember, molarity is moles per liter. So we had the molarity, 8.00 times 10 to the minus 2. We want to know how many moles. It was 0.25 liters, 250 milliliters. So the number of moles would be 8.00 times 10 to the minus 2 times 0.25. So 2 times 10 to the minus 2 moles. Similarly for number 2, number 3, and number 4, all you do is take the concentration and multiply it by the volume. It'll tell you the number of moles. So now, of course, if you have the number of moles, you can figure out the number of grams if you know the molar mass of the solution, of the substance. Questions? You okay with that? So, back to stoichiometry. Yay. Solution stoichiometry. Here we have sodium sulfate dissolved in water. We get 2 Na pluses and 1 SO4 2 minus. So if the solution is 0.35 molar in sodium sulfate, it's actually 0.7 molar in Na plus. Why? Because of the 2, the stoichiometry. For every Na2SO4, we get 2 NAs. So if I have 0.35 Na2SO4s, I have 0.7 Na pluses. But I only have 0.35 SO4 2 minuses. It all has to do with the stoichiometry. And you see we have the Na plus in brackets. When you do that, that means concentration. That's an abbreviation. So if I put the Na plus in brackets, it means the concentration of the sodium ion. So if I look at AlCl3, and it's 1.02 molar, what would be the concentration of the chloride ion? In AlCl3. Well, what's AlCl3 going to break up into? Yeah, how many? It's going to break up into ions. It's going to break up into Al 3 plus, Cl minus. How many Cls? 3. So if I start with 1.02 molar AlCl3, how many Cl minuses? Okay. It would be 3.06. 3 times that. I get 3 Cls for each AlCl3. Nitrate ion in the solution of 0.451 molar calcium nitrate. So calcium nitrate is going to break up into calcium and nitrate. Yeah, okay. Let's not make this harder than it needs to be. How many nitrates are we going to get? 2. 2 NO3s. Remember, that's 1 unit. So what is the concentration of nitrate in that solution? If it's 0.451 in calcium nitrate, we say we get 2 nitrates for each calcium nitrate, so what's the concentration of the nitrate going to be? 2 times that, yeah, good. So 0.902. Okay, Na2CO3. I want to know the concentration of sodium carbonate. It is in Na plus. It is 0.124 molar. So what's the concentration of Na2CO3? Yeah, 0.062. Why? Got to divide by 2, exactly. Yeah, that one's going the opposite way. We get there's 2 sodiums in sodium carbonate, so we got to take the sodium and divide it by 2. So the first one was 3.06, second one was 0.902, and 0.0620. So again, later on in CHM152, this will come into play when we do what's called colligative properties, which are fun. I like colligative properties. Some of them are depressing. Freezing point depression. Now we're going to look at some analytical techniques, gravimetric analysis, acid-base titrations, and redox titrations. Now you had some experience with gravimetric analysis in the separation of mixture. We're actually going to precipitate something in a reaction, weigh the precipitate, and from that we're going to find out how much is in the sample. So gravimetric, kind of like the sauce, based on mass, gravity. So here we have 0.8633 gram sample of ionic compound containing chloride ions, and an unknown metal cation is dissolved in water treated with excess silver nitrate. Okay. So here we have 0.8633 grams of some ionic compound. So we have some metal. I'll call it M for metal. We don't know what it is. And it contains chloride ions, so we know we have some Cl in there. We're going to treat it, let me write equation, so I'll write MCl. We're going to treat it with silver nitrate. So we're going to get some metal nitrate plus silver chloride. Well, this was dissolved in water, so this is the MCl is aqueous. The silver nitrate is aqueous. The metal nitrate, from our solubility rules, nitrates are always soluble, so that's going to be aqueous. The silver chloride is not soluble, so it's going to precipitate. So now we have a precipitate, silver chloride. We filter it, dry it, and weigh it. And we find out that we have 1.5615 grams of silver chloride. What's the percent mass of chlorine in the original compound? Uh-oh. You have to think about this. So here's our original compound. We're going to do percent chlorine. How would I do percent chlorine, just in general? It would be in a sample, it would be the weight of the, no, it would be the weight of a certain sample, chlorine. How do you do your percent composition? in the mixtures. Part over the whole, so I need to know the weight of the, what would be the part? What's the part I'm looking for? No, what's the part I'm looking for? Chlorine. So it'd be the weight of the chlorine. What's the whole part? The weight of the metal chloride. What's the weight of the metal chloride? This is the weight. I told you, yeah, that's the weight. 0.8633 times 100. So we need to know the weight of the chlorine. Well, here's a sample of chlorine, silver chloride. Where did all this chlorine come from? It came from the metal, right? So we just have to figure out how much chlorine, how much of this weight, the 1.5615, is chlorine. How do we do that? Not quite. How much of silver chloride is chlorine? What percentage of silver chloride is chlorine? No. We're going to do percent. Again, percent chlorine. Now we're not talking about this, we're talking about silver chloride. So if I'm going to do the composition of silver chloride, what would it be? For chlorine, it would be the weight of chlorine from the atomic periodic table, which is 35.45, over the weight of silver chloride. Silver chloride weighs altogether 143.35. Adding the silver and the chlorine together. Times 100. So what's the percentage of chlorine? 24.73%. Right? Everybody with me so far? Everybody's got lost yet? Okay. So we know we have 1.5615 grams of silver chloride. I want to know how much is chlorine. I know, put the 100 here, 24.73%. So now I figure out for X, and I get X to be
0.3862.
I do the plug and chug. It's 0.3862 grams. So you said 0.3862? Okay, so now I got the chlorine. Now I go back over here, 0.3862. That was the chlorine. The way the sample is 0.8633. The percent chlorine now is 44 what? 44.73. Let's see if you were right. All right, 24.73, that's the percent of chlorine in silver chloride. And then you use that to figure out 0.3862 grams, 44.73. We didn't identify the metal, but we can kind of narrow the possibilities down. So this is a case where you were given enough information to solve the problem, but you had to use two different equations, well, same equation two different ways, and realize where the answer comes from, what you need for one equation, and how to get that information from the second equation. And that's a lot of what chemistry does. That's a lot of what, when you go out and start working, whatever you're working in what field, that's what it's about, solving problems. Very seldom you get one equation per problem. A whole bunch of things you got to put together, come up with a solution. find your way? Usually I get people. Okay, questions about it? No? Okay. I always ask, and people always say no, and then, I give the test, and I let it go. Yeah, apparently there were a lot of questions, because the grades don't reflect that. So, acid-base titrations. A titration, we take a standard solution where we know the concentration, and we add it to another solution of unknown concentration until the reaction is complete. So if you know the volumes of the standard and unknown, you can figure out the concentration of the unknown. Sounds a lot more difficult than it is. So a lot of times what we use as the standard is a solution of a strong base with a known concentration. Sodium hydroxide. To do that, we must standardize. Because sodium hydroxide in solution reacts with carbon dioxide in the air, making the concentration unstable over time. So before we use it, we have to standardize it so we know its exact concentration. Even though sodium hydroxide is a solid, and we can weigh it out and dilute it in a certain volume and say, oh, it's this concentration. Yeah, technically you're right, but if you don't use it for a week, it might not be that concentration anymore. So we're going to titrate it against an acid solution of accurately known concentration. What they normally use is this compound called potassium hydrogen phthalate. There's this picture. It has one ionizable hydrogen, a little white ball there attached to the oxygen. So it reacts with sodium hydroxide. It is a solid. Normally, if you do it, take on a little bit of chemistry, you have to dry the potassium hydrogen phthalate in an oven to what's known as constant weight. So that means the lab could take up to several days to do, because you heat it in an oven at a high temperature, take it out, wait for it to cool, weigh it. Then you reheat it. Take it out, cool it, weigh it again. And you have to do that till the weights come out to be within like 2 milligrams of each other. It can take a while. So here what we do is dissolve a known amount of potassium hydrogen phthalate in a known amount of water, so we know its concentration. In the burette, which is the thing at the top there, which is kind of like a long graduated cylinder with a stopcock on it, we have the sodium hydroxide solution. We drip it into the acid solution. The acid solution also has phenolphthalein indicator in there, which is clear when it's acid, pink when it turns basic. So you start adding the base to the acid, start neutralizing the acid. It reacts. Once we completely neutralize it, the next little half a drop of base turns the solution basic, and it'll go to a pink color. So that's when we're done. It's called the end point. Or the equivalence point. So phenolphthalein, there's a whole bunch of different indicators we use, but phenolphthalein is routinely used. And you'll probably do one near the end of the semester. So here's our problem. Student finds that 25.49 milliliters of an NaOH solution is needed to neutralize 0.7137 grams of potassium hydrogen phosphate. What's the concentration of the sodium hydroxide? So there's the molar mass of potassium hydrogen phthalate, 204.2 grams per mole. So you need to know how many moles of KHP we have. So the moles of KHP would be the 0.7137 grams divided by the molar mass. We end up having 0.003495 moles. Well, to neutralize that, we need the same number of moles of sodium hydroxide. So we need 0.003495 moles of sodium hydroxide. Okay? To figure out the concentration of the solution, molarity is moles over liters. So we have 0.003495 moles divided by 0.02549 liters. The 0.02549 liters, if you remember, 25.49 milliliters was used to titrate. That's where the liters came from. We converted the milliliters to liters. So the concentration of the sodium hydroxide solution is 0.1371 molar. Yes? No? Maybe? Remember I said we're going to be using stoichiometry the rest of the year, so we went from grams to moles. Now we use the concentration to figure out the molarity.
When the pH is different
I'm sorry, when the pH is different where?
between the two compounds. If it's not like a proportionate base or acid to base.
I'm not sure I know what you're asking.
If like you have a pH of 1 and you're titrating a pH of like 14.
No, the way this works is, okay, you got the acid dissolved in water. So you're going to have an acidic pH. You're going to have something below 7. It could be 1, it could be 2, depending on the acid you use. The base is going to be above 7. Sodium hydroxide is usually around 12. So when you hit neutral pH is 7. They start reacting. The pH slowly goes up, and you hit 7. As soon as that next little drop goes over, especially with a strong base, it's going to jump up to around 9 or 10. That phenolphthalein is going to change color just like that. That's and it turns pink. And that's what you've done. So here, what volume in milliliters of a 0.203 molar NaOH solution is needed to neutralize 25 mils of a 0.188 molar sulfuric acid solution? I'm going to show you a quick way of doing this. We can go through all the moles and millimoles, but I'm going to show you a real quick way. Remember our dilutions calculation? Concentrated molarity times the concentrated volume is equal to the diluted molarity times the diluted volume. Well, I'm going to change these subscripts. The molarity of the H plus, you wrote it down, I got to erase it, right? Yeah, get that. Is equal to the liters of the H plus. The molarity is the OH minus. The liters of the OH minus. So if I look at the top here, we have 0.203 molar NaOH. And we have 0.188 molar H2SO4. We have 25 milliliters of that. So I want to know how many milliliters of this, the NaOH, I need to neutralize the acid. So what's the molarity of the H plus for the H2SO4? How many H pluses am I going to have for the H2SO4? 2, right? Remember what we did before with the aluminum chloride in that? So its molarity in terms of H plus is going to be 2 times that. 0.376. What's the volume? And you can leave it in milliliters, 25 milliliters. This could also be milliliters as long as it's the same. What's the molarity of the sodium hydroxide? What's the molarity of sodium hydroxide? 0.203. Because how many OHs are in sodium hydroxide? 1. So the molarity of the OH minus is going to be the same as the molarity of the NaOH. And we want to know its volume. So its volume would equal 0.376 times 25 divided by 0.203, whatever that comes out to be. I'm too lazy to do it. Somebody's going to tell me. I'm what? 46.3. Okay, that's the way, I like the short way. Because you can see from the balanced equation, for every millimole of sulfuric acid, we need 2 millimoles of sodium hydroxide, because it's stoichiometry, 2 to 1. So they go through millimoles and moles, back to volume, and they end up at 46.3. So they go through all of that, and we just use this little adaptation for the dilution to do the same thing. As long as you remember we're talking about H plus and OH minus. You can do it either way. I kind of like this way because I don't have to think too much about millimoles and going back and forth and all around. So let me change things up here a little bit. Let me give you another. So I have 105 molar barium hydroxide, and let's say I have 25 milliliters of this that I use in the titration. And the volume of, I have HCl, acid, and I had 50.0 milliliters of this. What's its concentration? So, what's the MH plus is what? In this case. What? L. What's the molarity of the HCl? We don't know, so it's MH plus. How much of it did we have? How much HCl did we have? 50. What's the concentration of OH minus?
0.21.
How'd you get 0.21? I didn't say it was wrong. I just asked you how you got it. Why'd you multiply it by 2? Oh, there's 2 OHs in barium hydroxide, so I got to multiply by that 2. 0.21. How much did we have? There's where the 25 comes in. So then the molarity of the H plus is got to be 0.21 times 25 divided by 50 Well, yeah. Wow, it's the same molarity. Does that make sense? Really? We said this is twice as much OH than this, right?
Oh.
But we're using twice as much volume of this than this. That makes perfect sense. Yes? No? Here, because we have two OHs here. That's 2 times 0.105, which is 0.21. So as long as you remember we're talking about H pluses and OH minuses, not necessarily what's written here, because this has 2 OHs, this only has 1 H. Let's do one more. Actually, I'm going to stop the recording because people are listening to this. Where's my little... So here's another problem. 0.1216 gram of a monoprotic acid is dissolved in 25 mils of water. Then the resulting solution is titrated with 0.1104 molar NaOH solution. You need 12.5 milliliters of the base required to neutralize the acid. What is the molar mass of the acid? So we want to know what the molar mass of the acid is. So molar mass is equal in general to what? It's equal to how many grams in 1 mole. So it's equal to grams per mole. So do we have the grams of the acid? It's 0.1216. Do we have the moles of the acid? No. But we titrated it. So we had how much of, what was the solution of the acid? What's the volume of the solution of the acid? 25 milliliters. Remember the molarity of the H plus, I'm going to use volume of the H plus, is equal to the molarity of the OH minus times the volume of the OH minus. We don't know the molarity of the H plus. What's the molarity of the base? Okay, 0.1104 molar. How much of it did we use? 12.5 milliliters. So the molarity of the acid is equal to 0.1104 times 12.5 divided by 25. So the molarity of the H plus is better be half 0.0552, right? So that's the molarity of the acid. Do we have moles of acid? No, we still don't have the moles of acid. But we know molarity is equal to, definition of molarity, moles of solute per liters of solution. So molarity we know the molarity is 0.0552 moles per liter. We don't know how many moles. Do we know how many liters of solution we have? What do we dissolve the acid in? How many liters is 25 milliliters? Yes. 0.025. So the number of moles is 0.0552 times 0.025, which somebody will tell me. Is that right? Is that what you said? 0.00138. So now we have the number of moles. Come back over here. We have the grams. Now we have the number of moles, 0.00138 moles. So the molar mass is 0.1216 divided by 0.0138. Drum roll. The calculator people are falling behind on the job. 88 what? 88.11. 88.12 grams per mole. See how you did it. Oh, very good. So once again, that's one of those problems where we had the information, we need to solve it, but it wasn't like you're used to seeing it. Here's two parts of the equation. What's the third part? You need to bring back everything you need to know about how do you get from point A to point B. So these are what we call critical thinking questions. Other people call it life. Sorry. Questions about that? Does everybody see the strategy? Everybody's all right with that? All right, I think we will stop there. Yay!